The plan for this lesson is to study dispersion measures and correlation. Namely, we will review the variance, standard deviation, covariance, and correlation. On a high level, the variance measures the dispersion or how the data are spread from the center of the distribution. The standard deviation is the square root of the variance. So if the variance and standard deviation are low, that means that the observations are too close to the mean. On the other hand, larger variance and standard deviation would mean that the data points are more spread out from the center, which also means more variability and wider range of values. Here are the formulas to compute the variance and, by extension, the standard deviation. So what happens here, we find the deviations from the mean, square them, and find the average. So in other words, the variance is the average of squared deviations from the mean. It's important to note that there are two variances and two standard deviations, one for the entire population and the other for the sample. Now it's a good time to discuss some properties of the normal distribution with mean mu and standard deviation sigma. I'm going to focus on the red and the blue because they have the same center but different spread of the distribution. Suppose the red curve represents the grades distribution in the algorithm's course, and the blue curve represents the grades distribution in the data mining course. So on a high level, which course seems to have better grades, although both have the same center or mean? So the data mining course is going to have better grades because it seems all of the grades are close to the mean. In the red curve or the algorithm's course, the spread is going to be larger and the range of the grades are going to be wider in both sides, but you don't want to be on the lower end of things, right? The formula we just discussed to compute the variance is correct and totally fine. However, from a purely system and implementation point of view, the formula makes unnecessary intermediate steps. So for incremental, scalable, and efficient computations, if we rewrite it in a different form, we are not going to run into these issues. I should note that compilers are getting better in this aspect, but to be in the safe side, I would code my programs in the best ways. So now we get to a question to test our understanding. Why square the deviations when computing the variance? There are many reasons why to choose squaring the deviations method over something else, like taking the absolute values. This method will make the variance insensitive to the direction, avoid the zero sum, and also it's going to give more weight to the larger deviations, so we can detect the spread of the distribution. However, on the negative side, if we do the square deviations and amplify the larger deviations, this method is going to be less sensitive to smaller changes in the data. Another question, what is the difference between dispersion and skewness? So dispersion measures the overall spread or the variability from the data. In other words, we're answering how much data points deviate from the mean. On the other hand, skewness measures the asymmetry or the direction of the data. Is the concentration on the right side or the left side of the mean? Covariance measures the linear relationship between two variables. So when we compute covariance, we gain insights into the linear relationship between those two variables, whether it has positive, negative, or no trend. Let's say we have a set of observations called A. This is how it looks like when we only have values for one attribute. Now, let's introduce a second attribute B. As you can see, everything in blue belongs to A and everything in brown belongs to B. To compute the covariance, we measure data as pairs, which means take 1 and 3 together as one observation. Similarly, 6 and 5, 10 and 15, and so on. So we start by finding the expected values for the first attribute, then for the second attribute, then finding the deviations for each observation, multiplying them, and computing the average. There are some issues with the covariance. It doesn't provide insights into the strength of the relationship between the attributes. It will only say that there is a trend, but it doesn't say anything how strong this trend is. Another issue, covariance is sensitive to scale. As you can see, multiplying the attributes by 2 change the value of the covariance dramatically, and I don't know how to interpret this outcome. So, recognizing the limitations of covariance, it becomes clear that a new measure is needed, and this is where correlation steps in. Dividing the covariance by the standard deviations of A and B is going to scale the covariance to an interval of -1 and 1, which will provide a comprehensive understanding of the relationship between those two variables. Positive correlation means when the values of one attribute increase, the values of the other attribute also increase. So a correlation value that is closer to 1 is going to tell us this is a strong relationship. Negative correlation means when the values of one attribute decrease, the values of the other attribute will also decrease. Finally, uncorrelated values when correlation equals to 0, which means there is no linear relationship. One last note, correlation does not mean causation. In summary, we covered data dispersion measures, variance, standard deviation, covariance, and correlation.